Hey everyone, today we're diving into a really brilliant analytical technique called conductometry. It's an incredibly clever way of using simple electricity to see what's dissolved in a liquid, even when it's totally invisible to the naked eye. So let's get right into it.
So here's the big question, right? How on earth can we use something as basic as an electric current to figure out what's hiding in a solution? I know, it sounds a little bit like a magic trick, but as you're about to see, it's just pure, elegant science.
All right, first things first, let's set the stage. Imagine you're a scientist. Maybe you're working in pharmaceutical quality control, and you're staring at a beaker of what looks like perfectly clear, pure water. But is it really just water?
See, that's the real challenge. Your eyes can totally fool you. That clear liquid could hold the exact concentration of a life-saving drug, or it could be contaminated with a dangerous impurity. You absolutely have to know the precise amount of whatever's dissolved in there, and we call those dissolved things analytes. And this is where our hero, electricity, enters the picture. Conductometry gives us this wonderfully elegant and really powerful way to solve this problem just by measuring how well that solution can carry an electric current.
So what is conductometry? Well, in a nutshell, it's a method that measures the electrical conductivity of a solution. And here's the absolute key. That conductivity is directly connected to the concentration of ions. The tiny, dissolved, electrically charged particles that are zipping around inside that liquid.
The principle behind it all is actually surprisingly simple. So first, we know our solution has these charged particles, these ions. Second, when you introduce an electric field, those ions start to move. Third, that movement of charged particles is an electric current that we can measure. And finally, this is the punchline. The more ions you have, the stronger that current is going to be. It's that direct relationship. And you know what? This entire process, this whole idea, is governed by a fundamental law of physics that you've definitely heard of before. Good old Ohm's law. Ohm's law gives us this beautiful, simple relationship. Current equals voltage divided by resistance. Now, to make that make sense, just think of water flowing through a pipe. The voltage, that's like the water pressure pushing everything forward. The resistance, that's how narrow or clogged the pipe is. And the current, well, that's the actual amount of water getting through. In our solution, it's the ions that determine the resistance. Okay, so we get the principle. We get the why. Now let's talk about the how. What are the actual tools of the trade? Let's take a look at the toolkit. Okay, the heart of the whole setup is something called the conductivity cell. It's basically a special container that holds our sample. And dipping into that sample are two platinum electrodes. They're what create the electric field. Oh, and here's a really critical detail. You have to keep the temperature perfectly constant, because temperature can change how fast the ions move, and that would totally throw off our measurements. So if the cell is the heart, then the brain of the operation is what's called a Wheatstone bridge. You can think of it as an incredibly sensitive balancing scale, but for electricity. It's a clever circuit that lets us measure the unknown resistance of our solution with extreme precision. It's what makes the data we get so incredibly reliable. Now for the really cool part. Let's see how this whole toolkit comes together in a common procedure called conductometric titration. This is where the technique truly shines. So in a titration, we're slowly adding a second liquid drop by drop into our sample. At the beginning, our solution is full of its original ions, so the conductivity is pretty high. But as we add the new liquid, a reaction happens that starts removing those ions, so the conductivity starts to drop. And then you hit this critical moment, the endpoint. Once all the original ions are gone, any extra stuff we add just introduces new ions, and bam, the conductivity starts shooting back up. It creates this really sharp, dramatic change. And the most beautiful part is what happens when you plot this on a graph. You get this unmistakable, sharp, V-shaped curve. That pointy bit at the very bottom of the V, that's not just some dip, that is the exact undeniable endpoint of the reaction. It completely takes all the guesswork out of it. It's just there, crystal clear.
So this is all very clever science, right? But why does it actually matter? What makes this method such a go-to technique for scientists in the real world?
Well, the advantages are huge. For one, it's incredibly accurate and precise. And because you find the endpoint on a graph, it basically eliminates human error. But for me, the real game changer is its versatility. You can use it on colored solutions, on cloudy or murky solutions, places where you could never just use your eyes. And on top of all that, it's so sensitive it works even when your solutions are very, very dilute. And trust me, this isn't just stuck in some research lab. The applications are literally all around us. It's used for everything from checking the purity of our drinking water to measuring the saltiness of the ocean for climate studies to all sorts of chemical analyses. And of course, like we mentioned, it's absolutely vital for quality control in the pharmaceutical industry, making sure medicines are both safe and effective. And that kind of brings us to a final thought, doesn't it? Conductometry is this amazing example of how we can use a fundamental force like electricity to see a world that's otherwise hidden from us. It really makes you wonder, if we can do all this with just a simple electric current, what other invisible worlds are we going to unlock as we get better and better at using the basic forces of nature?